Good evening, everyone. Welcome to our Stargazing lecture for December, the final one of 2020. I'm Dr. Cameron Hummels. I'm a computational astrophysicist at Caltech, and I will be your host this evening. So welcome. We have a super fun event tonight. It'll consist of, after some announcements by me and a little bit of looking up at the sky, at least virtually, I'll introduce our speaker for tonight, Vikram Ravi, who's a young professor in the department. He will give a presentation for about 30 minutes on radio astronomy, which is going to be super cool. And then we will go straight into a Q&A panel. So both Vikram and myself and two other members of the department who work on other fields of research will be answering your questions, not just on the content of Vikram's presentation, but on whatever space and astronomy and physics questions that you may have for us. So I encourage you guys to, throughout Vikram's presentation, and then during the Q&A, write your questions in the YouTube comment section of this the YouTube chat during this event, and we will try to answer them as best we can. So let's see. These events happen once a month, like tonight, on a Friday evening. When they're in person, we have a stargazing component that hasn't really been possible, although I'm working on it, and hopefully by next month we may have the ability to do some virtual, actual astronomical observing, where I set up a telescope and then we try and look at various different things in the sky. I don't know how well it's going to work, but I'm going to give it a shot. So stay tuned on that front. We have a sister series of events going on called Astronomy on Tap. These are less formal events consisting of two 15-minute presentations by different researchers in the field of astronomy, both at Caltech in LA as well as globally. Now that the pandemic is going on, we can get people from all around the world to participate and give presentations. Our next one, these always happen on Monday evenings, and our next one is happening a week from this coming Monday on December 14th at 7:30 p.m. And it will be on the topic of primarily on solar system stuff, specifically comets and meteorites and meteors, to coincide with the Geminid meteor shower that's happening. The Geminids, named after the constellation of Gemini, because that's where they appear to all come from. These meteors, this meteor shower is going to be kind of the biggest meteor shower of the year because it coincides with a new moon. So when you don't have the moon in the sky, that's obviously quite bright, it allows you to see fainter and fainter objects that are in the sky. And since shooting stars, meteors can be bright, but oftentimes they aren't quite so bright, it'll allow you to see more of them. So the frequency is probably going to be on the order of once or twice a minute, depending on the conditions under which you're seeing it. But again, this is kind of peaking on the 13th and the 14th of December in a week and a half. So it should be really cool. Other announcements. We will continue to have these events once a month through 2021. I'm putting together the schedule right now. I haven't yet announced it because I don't yet know when the dates are or who's going to be speaking, but we'll both have the Stargazing lecture series that will continue to go virtually for probably at least the first 6 months of 2021, maybe longer. I don't know. It's going to depend on what the state of the world is under that timescale, but we'll have that as well as Astronomy on Tap going through the foreseeable future. So I'll continue to update our website at Caltech Astronomy Outreach, as well as the YouTube page, as well as social media, blah, 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 all these different sources. So I encourage you guys to keep checking these things out as we move forward. And if you're really excited, if you're really excited about these events, all of our previous Stargazing lectures are recorded and on our YouTube page, so you can scroll down and check out different topics from the past, because we've had some really, really good speakers and great content that's been given over the last 5 years that we've been doing this. So I encourage you to check it out. Okay, so these events always coincide with some sort of stargazing component. As I said, we can't necessarily do stargazing in reality, but I'm trying to do it. Oh no, where did my, Okay. I'm trying to do it somehow virtually. I'm using this program called Stellarium, which is a sky visualization tool. It's free, it's open source, it works on a variety of different platforms. I encourage you to download it and check it out and play with it yourself. So this is showing what the sky looks like tonight at this moment from here at the location in Pasadena, although we probably have more sky brightness, so we probably can't see all these stars from here, but this is where they would look if we had great viewing conditions. You can see there's this red dot kind of near the zenith. That's Mars. And if we zoom in on Mars, which you could effectively do if you had a decent telescope, you'd be able to see some of the structure of Mars. It's challenging unless you have probably a 10 or 12-inch telescope and maybe a pretty good eyepiece and the ability to track it to be able to see some of this structure. But Mars is definitely up there, and you can see it naked eye if you just look in kind of the southern part of the sky near the zenith. Another thing, I don't want to take too long on this. We could spend all night just looking at the various different objects that are visible in the sky, but you can just see Orion is rising on the eastern horizon, which is quite identifiable because the 3 stars in the belt, and then Betelgeuse and Rigel and the structure here of Orion. But let's not talk about Orion. We're going to use Orion as a pointer, and it points through the Hyades here towards this object. Now, this object is the star cluster known as the Pleiades. It's also known as the Seven Sisters. And if you zoom in, you can see something like this. And you can see this even with kind of a good grade binoculars or even a reasonably small telescope, be able to see some of the structure here. So it's a star cluster that's about 400 light years away. It has several bright stars in it that are blue giant stars, but it also has something like 1,000 members of the cluster as a whole. It's about 100 million years old, which is reasonably young by star ages, and it's just beautiful. It's one of the most beautiful things to look at in the sky, in my opinion. And you might also recognize it. It looks kind of like a little Big Dipper here, but that's just a coincidence. You might also recognize it because, let's see if I can share. Because it is the Subaru emblem. The car company, the Japanese car company, Subaru, chose it as their emblem. Oh, I'm not sharing right now. I need to, there we go. There, it is the car company's emblem, because this is, this is the name for that object in the sky in Japanese culture. The car emblem is because several different companies kind of collaborated and formed. 6 different companies came together to form a single company, so they called it Subaru. But it's this star cluster, so I think that's pretty interesting. Anyway, those are all the kind of stargazing things that I wanted to point out. But Vikram, can I get you to come on here?
There we go. Hi, everyone.
Oh, excellent. Excellent. Good to see you, sir.
See you too.
So Vikram is, well, I guess I'll just jump right into my introduction for you. Dr. Vikram Ravi is an assistant professor of astronomy at Caltech. He builds and uses telescopes to study the hidden parts of the universe, such as objects that are visible only for milliseconds and matter that is otherwise dark. He's a passionate educator and also enjoys the outdoors, music making, food, and travel to far-flung parts of the world. Yeah, I'm really excited about your talk, Vikram. And yeah, I guess I'll just let you take it away from there.
All right, let's get going. Thanks everyone for joining us tonight. I know it's a Friday night, and hopefully this can be a bit of entertainment as well as something interesting and educational for you today. So I would like to tell you all about basically the kind of astronomy that I do here at Caltech. trying to answer really big questions by building various kinds of telescopes that sometimes catch sort of the fastest phenomena in the night sky. Now, the telescopes that I build are radio telescopes. Now, you've all, I'm sure, somewhere or the other seen pictures like these. This is, in fact, a cluster of galaxies. This is a region that is forming very young stars within our own Milky Way. And this over here is the core of the giant galaxy M87, which may be familiar to those of you who were here for last month's talk by Professor Katie Bauman. Now, let's ask the question about what this would look like if you could see with radio waves. Well, let's get going. So first of all, if you pointed a radio telescope at this cluster over here, what you would actually see are these amazing multicolored filaments of basically extremely hot plasma. In fact, plasma is so hot that the electrons are moving at relativistic speeds, spiraling around magnetic fields, sort of stringing the space between galaxies and emitting radiation that we then observe with radio telescopes. So far, so good. What about this one? Well, if we were to point a very large telescope at this star right in the middle of this star-forming region called HL tau, you would actually observe the formation of baby planets. These disks in these rings in this disk of dust are actually evacuated by planets in the very earliest stages of their formation. These are actually planets in the process of forming before our very eyes. And finally, of course, it will come as no surprise that when you point a very large collection of telescopes at the core of the galaxy M87, you observe this ring of radiation glowing around the supermassive black hole right in its center. Just to remind you all, the size of this thing is roughly the size of the solar system, even though this galaxy is something like 50 million light years away. This sort of angular resolution, this sort of ability to resolve really small features, is one of the many really amazing things about radio astronomy. Now, radio telescopes that you may be familiar with look like these. Of course, the one on the top right over here is the Very Large Array of contact fame. The one over here on the top left is the Atacama Large Millimeter Array, or ALMA, in Chile, which is a large collaboration between countries in North America and Europe and East Asia to build this amazingly powerful array of millimeter wave radio telescopes that actually see galaxies close to the very edge of the observable universe. Then we have a telescope that is very dear to my heart. As you may be able to tell from my accent, I am from Australia originally, and I spent a lot of time during my graduate school sitting in the tower of this telescope here called the Parkes telescope. This, if you're particularly into astro movies, I recommend a movie called The Dish. It tells the story of how the Parkes telescope was the first telescope to actually receive the video signals from Neil Armstrong landing on the moon. And finally, of course, it's kind of pains me to show this photo, but of course, this is the Arecibo Observatory, which unfortunately recently suffered a collapse, but which I would really like to highlight here, the many discoveries that it has made throughout its history, one of which is coming up right now. So radio astronomy is, of course, sort of delivered its fair share of amazing discoveries throughout history. Quasars, or the shining supermassive black holes throughout the universe, were discovered with radio telescopes, as was the faint echo of radiation from the Big Bang, known as the cosmic microwave background, as were pulsars. This, of course, being a famous cover from a Joy Division album, which you see on t-shirts. It also happens to be the pulsar B0329 plus 54, which is among the top roughly 5 brightest pulsars in the sky, depending, of course, on when you look at it. And finally, we have evidence for gravitational waves which was actually discovered at the Arecibo telescope when astronomers Joe Taylor and Russell Hulse and Joel Weisberg traced the orbit of a pulsar around its white dwarf companion to show that the orbit was actually decaying due to the emission of gravitational radiation. Radio astronomy has done some really cool stuff, but what are we actually doing now? Well, one of the things I'd really like to highlight in this talk and really bring home to you through the course of what I say is that although we have done an amazing job, I think, over the last several millennia, really, as long as astronomers have been doing astronomy, to try and push our understanding of the universe further and further in space and further back in time, there is still an amazing amount that we don't know about the universe that we live in. So first of all, this again may be familiar to some of you, but it's really mind-boggling to me that if we start with dark energy, which forms about 68.5% of the effective mass density of the universe, we don't know what that is. Then, I'm scaling this according to mass. Dark matter forming about 26.5% of mass density of the universe. We don't know what that is. Even visible matter, which forms about 5% of the universe. This is, of course, star football player Aaron Donald. Even among the visible matter, the matter that we actually observe with most of our telescopes forms less than 1% of the matter in the universe. The matter that makes up you and me and everyone else in this call and your computers that you're watching this on, that's less than 1% of the matter in the universe. So where is the rest of it? Well, the story is really it's the story of how we got here. It's a story of how galaxies formed out of the original soup of hydrogen and helium, how stars formed within those galaxies, how those stars died, enriching the universe with metals, and how new stars formed and formed planets and thus formed humans. What we see here is a simulation on the left of the evolution of the dark matter field in a box that is representative of the universe. And on the right, we see the temperature of gas. This is gas that is normal matter. This is visible matter like you and me. And you can see that as the universe evolves, you sort of see that the normal matter, the gas, starts to coalesce in the nodes of this cosmic web. And if you're looking really closely, you will also note explosions of red, which in this case is really hot and diffuse material. These explosions of this material into the intergalactic medium. Each of these explosions is driven by the ignition of a supermassive black hole. Matter falling onto a black hole gets really hot and is expelled into the intergalactic medium as these big red bubbles. And what you can see as the universe evolves to the present day, we're currently still only 9 billion years after the Big Bang, still a long way to go. You can see that the universe is getting hotter and hotter and hotter and more diffuse. This is why we cannot observe most of even the normal matter in the universe. It's because it is so hot at temperatures well over 1 million degrees centigrade, so hot that no telescopes that we currently have can actually observe the light that is emitted from it. I'm just going to pause this here. And it's also so diffuse that, in fact, it's something to the order of a few atoms per cubic meter, that no telescope, you just cannot build up enough of a column of it to actually observe even sort of in absorption towards distant sources. This is a really difficult problem, observing this diffuse matter in the universe. Fortunately, however, we've recently found a way of doing this. And it comes in sort of a very unlikely form. Now, taking a complete turn away from what I was talking about a minute ago, the way that we can observe this matter is actually by using some of the brightest and fastest phenomena in the sky known as fast radio bursts. So what are they? Well, for a long time, astronomers have been trying to observe pulsars. I told you a bit before about how pulsars were used to find evidence for gravitational radiation. In trying to observe pulsars, what we also found were these amazingly unusual bursts of radio waves that apparently come from distant galaxies. What do they look like? Well, hold on to your seat because this is what they're like in real time. Here we go. Whoop, there they went. That just flashed right by your eyes, right? So let's do that a bit more slowly. What you can see is as time goes by, we can see this swept burst of emission that starts up at higher radio frequencies and ends up at lower radio frequencies. This characteristic sweep of the pulse, we can actually use a very straightforward analysis. And this, I promise you, is the only equation in the talk. I find that some people who come to these talks really want to see an equation. And so if that is you, here it is. What we can do is a calculation where we multiply a typical distance through the universe of something like a gigaparsec by the typical density of the universe to get what we call a column density. So the density times a distance. And it just so turns out that radio waves passing through this really hot material that we think is flooding the universe will actually be delayed at lower radio frequencies by this matter. This effect is called dispersion, and it's exactly the same physics, as it turns out, as what causes a rainbow, or what causes the spreading of light into a spectrum by a prism. It's the same physics, the delay of radiation at lower and lower frequencies. And what we do is when we work out how delayed the radiation is, we actually find that it is consistent with having passed through a significant portion of the universe. We're using, by simply comparing the so-called dispersion measure with the predicted delay of the pulse. And so what we know of now that are these bursts of radio waves called fast radio bursts, or FRBs. We think there are roughly 1,000 of them happening over the whole sky every day. When you correct for the effect of the dispersion, when you line up all the radiation different frequencies, you find that the pulses last for something like a millisecond, often less than a millisecond. And we inferred distances of well over a gigaparsec in some cases. Their energies are something like 10 to the 32 joules, or roughly 10 to the 30, so 1 to 30 zeros after it, more energy than there is in the fastest tennis ball that's ever been served. And we also, as it turns out, although we know they come from really far away, we don't really know where they come from. We also don't know what makes them. Many mysteries here. But nonetheless, we do see evidence from that sweep of the propagation through this web of material in the intergalactic medium. We also see evidence for magnetic fields in the host galaxies, as well as the Milky Way. We also see evidence for actually multi-path propagation, that radiation didn't just come in one way, it took multiple paths to get here because it had to pass through different sort of blobs of material that deflected the radiation as it came to us. Nonetheless, we're left with some fundamental questions here. What are the sources of these mysterious fast radio bursts? And also, what is the nature of the medium through which they propagate? And these are the questions that my group here at Caltech, as well as collaborators around the world, are trying to solve. The latter question in particular has strong implications for the distribution of matter in the universe, as well as the nature of dark matter itself. What we're trying to do is to answer these questions by building instruments at Caltech's Owens Valley Radio Observatory. So the Owens Valley is a valley in Eastern California. It's pretty spectacular. If you haven't been up there, I strongly encourage you to get up there. It's near the town of Bishop on the way to Mammoth. And this panorama of OBRO shows you sort of the breadth of experiments that are underway up there. We have a large 40-meter diameter dish. This dish spends its days scanning and measuring the brightness of something like 1,800 active galactic nuclei, supermassive black holes, in order to find very unusual variations in their brightnesses. This dish over here is part of the Very Long Baseline Array, which is an array of radio telescopes spanning the United States from Hawaii all the way through to the US Virgin Islands. And they combine these dishes to make extremely high angular resolution images. These 6 dishes over here are millimeter wave dishes, which actually try to study star-forming regions, as well as the evolution of molecular gas throughout cosmic time. And there are a few other things, as we'll see in a minute. But first, some of you, the particular aficionados among you, will have seen a movie called The Arrival. Now, if you haven't seen it, I don't recommend it. It's not, but nonetheless, it does feature the Owens Valley Radio Observatory rather heavily. This is the 40-meter dish that you just saw. As you can see from the silhouette up here, there's a lot more going on up there than one might think. Anyways, if you feel like watching something else astronomical after this, I encourage you to find it. But if you do watch it or have watched it, you'll note somewhere in there that Charlie Sheen at one stage comes back to Pasadena and puts together a phased array of radio telescopes in order, as you might guess, I'm not giving anything away here, to find the aliens. That's what we did. Of course, not to find the aliens, but to find the fast radio bursts. And so while I was a postdoctoral fellow here at Caltech, myself and a group of researchers here put together an array of 10 of these dishes in order to pinpoint the locations of fast radio bursts. These dishes are exactly what they look like. They are literally satellite dishes. I found them on Alibaba.com. They were shipped for about $7,000 per dish. It's pretty doable, really. We, as you can see, assembled them. We designed our own radio receivers in the labs here at Caltech. We then, you can see, they just sort of arrived in shipping containers up at the observatory. But the point of the array was to scan a really large patch of the sky, about 7 by 7 degrees across. This is it roughly to scale, in order to find exactly where these fast radio bursts were coming from. And so we did this. This sort of gives you a sense of how many galaxies exist within a region that is 100th this size. And so you can see this sort of scanning a massive area, but having to find which of the galaxies like these might host the fast radio bursts. This is an image from the Keck Observatory on Mauna Kea in Hawaii. And the one that we found just before shutting down this particular experiment was in this galaxy right here. What you can see is, in this burst, the burst of radio waves, you can see that this is its radio spectrum. We've corrected for the effects of dispersion. And when we took a spectrum of the light from this galaxy with the Keck Observatory, we found that the host galaxy was, as far as we could tell, pretty much identical to the Milky Way. And yet it was 8 billion light years away. These little tiny dishes that came to us in shipping containers actually saw a burst of radio waves from 8 billion light years away. This, of course, means that it was first emitted 8 billion years ago. By tracing this burst back to this galaxy, we were able to measure the amount of mass between us and this galaxy, the amount of gas in the intergalactic medium. And in particular, if you squint really hard, you'll see that this galaxy appears to be in a little grouping of galaxies. As it turns out, it's a little bit behind this grouping of galaxies. And so we were actually able to say how much mass was associated with the group of galaxies. Besides, of course, saying that, I think just for the second time, what sort of galaxy a fast radio burst actually comes from. So another thing that we did along these lines was a graduate student working with myself and Professor Shri Kulkarni here at Caltech decided to take these radio receivers from the top of our dishes and just turn them upside down. Instead of pointing the receiver at the dish, he just decided to point them straight up. And he took 3 of them, put one at the Owens Valley, one in the Goldstone Deep Space Communication Center, and one at another site in Utah. And what he tried to do is, instead of trying to find these really distant fast radio bursts, he tried to find the nearest fast radio bursts. The idea being that by having these receivers at 3 different sites, you can actually reject locally generated signals because, of course, you expect the burst, if it exists, to actually be seen at all sites. And earlier this year, we were lucky enough to actually discover a really bright radio burst from within our own Milky Way. And what you can see here again is the burst radio waves at each of the 3 sites, as well as the radio spectrum at each of the sites. You can see that this is sort of why we really need 3 sites. If you just had the one, you might go, this looks a bit noisy. I don't know if I believe that. But the fact that it existed at all 3 sites was critical to us being able to show that this was real. As it turned out, we weren't the only ones to see it. A group in Canada also saw the same burst, but because we saw it pretty much overhead, we were able to say exactly how bright it was. And it was very, very bright. Let me spend a minute or so explaining this plot here. So what we're seeing here is basically the whole sort of gamut of types of radio things that vary in the sky. We can see stars like our sun, they put out radio bursts. We can see black holes that accrete matter from companion stars, they put out radio bursts. We can see supernovae and gamma ray bursts and active galactic nuclei and pulsars and rotating radio transients, they all put out radio bursts. These are the fast radio bursts. They're very bright and they're very short. And so they live all by themselves in this corner of this plot. And the burst that we found, which has this rather telephone number-like name, is as close to the fast radio bursts as anything else, and in fact is most comparable to fast radio bursts in its duration and energetics. And therefore we think that we have found a local analogue of the extragalactic FRBs. As it turns out, we also were able to trace it back to a specific and very special kind of star within the Milky Way. The star, that here's an artist's impression of it, is known as a magnetar. And these have the strongest magnetic fields that are known in the universe. And magnetars are the sort of collapsed remnants of supernovae. They're neutron stars. Neutron stars are, of course, these really dense and heavy objects. Pretty much your last stop on a black hole. But not being a black hole, of course, they can emit all sorts of things, and we see them across the electromagnetic spectrum. This result showed that we have a plausible way to make fast radio bursts. So where are we going with this? And so this whole, I guess, concept of buying these really inexpensive dishes or building these really inexpensive dishes and then equipping them with cutting-edge receivers as well as cutting-edge signal processing systems, we call this concept the Deep Synoptic Array. It was started off by another Caltech professor, Professor Greg Hallinan, in 2013. This is not Greg. This is another astronomer and really a giant of radio astronomy known as Sandy Weinreb, who spends a lot of his time designing radio receivers and radio feeds, but also was the first person to discover masers in space. This was the first dish we had for the program. When I came along in 2016, I led the construction of the DSA-10 array. 4 of the dishes are shown here. And now we're in the process of building a 110 element array known as the DSA-110. The DSA-110 is an expansion of the DSA-10. You can see that the dishes look a bit more sophisticated. They actually move automatically, which is an amazing thing for us. You can see many of them in a line over here. We will eventually have 110 covering the entire OVO site in order to pinpoint the origins of over 100 fast radio bursts each year. Early science operations actually commenced earlier this week. And so we expect the first fast radio bursts very soon. But what I want to leave you with is where we hope to go in the future. So we sort of went from 1 antenna to 10 antennas to 110 antennas. But if we really wanted to make a perfect picture of the radio sky, you might ask, how many antennas do we actually need? Is 10 enough? Is 100 enough? Where does it stop? I mean, so the Very Large Array of the VLA has 27, and in having 27, it turns out that they need to put in a lot of effort to actually process the data to make images. Let me show you why. So what I've done here is simulated observations with an array of 30 antennas, where these little dots over here kind of are just showing you the measurements made by the array. And on the right, I've reconstructed an image of something random that, and I've not done any further processing to it. I've not made any effort to account for example, the response of the instrument, where the antennas are, what their sensitivities are, and so on. I've not made any attempt to account for that. Now, you might look at this and think, yeah, it's a circle, right? It's just a circle. And you'd be right, because this is the true image. It's just a circle. If the images are simple, a few antennas are enough. However, if the images are not simple, you're in trouble. And what I've done here is taken an extremely complex image, an image so complex that even 30 antennas is not enough to figure out what it is. And you can see that it's just a mess, right? It's just a mess of stuff, and at least I can't see any pattern in there. As we add more antennas, you will see a pattern emerge. We're up to 250, 300, 350, 400, 450, 500, and now the pattern is pretty clear. It's our very own Dr. Cameron Hummels. And so as we loop through this again, you can see that as you add the antennas, the image gets clearer and clearer and clearer. Now, if I were to pause it right here, yeah, that's pretty good, right? I mean, you can see that it's Cameron, you can maybe even read the Caltech Astro badge over there, but you can still see it's kind of a bit blurry, and there's these weird lines across there, which maybe you could sort of clean in one way or the other. But we don't really want to do that, because we don't want to make any assumptions about what the sky truly is. And so that's why, for a future telescope, we think we actually need 2,000 antennas. I'll pause it right there, and you can sort of see the difference between that image with a few hundred antennas and 2,000 antennas. That's exactly what we hope to do in the future, is to build an array of 2,000 of these small antennas in order to survey the sky better than any radio telescope has ever surveyed the sky. What we're sort of showing here is a plot of the speed with which we can survey the sky, as well as angular resolution. And these are all the current or planned radio telescopes. And this is where our proposed instrument, the DSA 2000, lives. It will find 1 billion radio sources, increasing the total number of known radio sources by a factor of 500. It will also measure the distances and masses of 16 million galaxies, and also potentially make a map of the cosmic web on very large scales. But to me, I'm always, as an observational astronomer, as an instrument builder, I'm always excited most by new discoveries. So the discoveries that I presented today, the discovery of the host galaxy of a fast radio burst, as well as the source of a fast radio burst in the Milky Way, were enabled by combining low-cost hardware platforms with completely autonomous data analysis engines. Our telescopes analyzed the data and found the bursts. This coming decade will really be a decade of transformational astronomical surveys. Surveys such as in the infrared, with a satellite called SphereX, in the X-rays with something called E Rosita, with the Rubin Observatory and the Legacy Survey of Space and Time to be undertaken in Chile. This is going to absolutely transform our view of the sky and really democratize the way that we access the sky. With your laptop, you will have the cutting edge data. But with this deluge of data, I'd like to leave you with the thought that we really need to rethink the nature of discovery. How are we going to sift through all this data? How are we going to ask the right questions in order to find the things we want to find? And this is what we're really thinking about at the moment and hoping to do with the DSA 2000 as well. And I'm just going to leave you with a bit of footage of the DSA 110 telescope that we're currently building at OVO. Thank you very much.
Excellent presentation, Vikram. That was really great, except for the part where you use the image of me.
It turned out well at the end, though, I thought.
Evan and Michael, will you join us, please?
Hello, everyone.
Great, great. Okay, so wonderful presentation, Vikram. You explained a lot of complicated topics very plainly. I thought it was good, and we have a lot of good questions from our audience. Before we go any further, I'd like to have each of the members of our Q&A panel here, seen in front of you, to introduce themselves and what they work on, and then we'll go straight into addressing your questions, both for Vikram on the content of the talk, or on any kind of astronomy or astrophysics or space science related questions that we may be able to address. So Michael, would you like to introduce yourself and what you work on?
Okay, yeah, sure. So I'm an astronomy graduate student here at Caltech. I'm already in my 5th year. Wow, time passes fast. So I study the atmospheres of planets around other stars. And lately, I've mostly been focusing on small rocky planets. Planets like 55 Cancri E, which is like twice the size of the Earth, but 2,000 degrees. So, in terms of its characteristics, it's nothing like the Earth. So I'm taking these planets, measuring their atmospheric mass and measuring the atmospheric composition and their mass loss rate. I'm also a huge history buff. I especially like the history of ancient Rome.
Yeah, and you gave an excellent talk earlier this year. If you guys are interested, Michael gave one of these stargazing lectures in, was it July or August, perhaps?
Something like that.
A few months ago on the topic of Greek astronomy, and it was super awesome. So I encourage you to check that out. Evan, what's that?
September the 4th.
September the 4th. Okay, so it was more recent than that. Evan, would you like to introduce yourself as well, please?
Yeah, absolutely. Hello, everyone. My name is Evan Hayes Nunez. I am a second-year graduate student at Caltech Astronomy. Let's see, I was born and raised in Southern California. For those that are know the cities, I spent half my life in Carson, California, and then the latter half in Torrance. Let's see, I'm working with Evan Kirby currently, so we share the same first name. He's a great advisor, and we're working in the Galactic Archaeology group. And what I'm focusing on in particular is ways that we can help describe the chemical evolution of galaxies over time. And what this is really looking at for me in my particular work is how can we put constraints on the amount of metals that the very first stars that formed in the universe gave off when they exploded. And so this requires us to use these really cool exotic objects that if you're curious about, you can definitely ask during the Q&A. But it's been a blast. I'm also working on another project that's going to be focusing on a fairly isolated galaxy called NGC 3109. So I'm still in the very early parts of that project, but yeah, that's what I'm working on currently. It's nice to be here.
Awesome. Excellent. Thank you, Evan. And I'm Dr. Cameron Hummels. I am a postdoc in the department who primarily works on computational modeling of galaxies, and in particular, the low density gas that surrounds galaxies, and is related to some of the stuff that Vikram was talking about in his talk, in terms of the distribution of this matter and what impact that plays on the signal coming from these distant fast radio bursts as it approaches us, and what those FRBs can tell us about the distribution of that matter and the phase and the temperature and the density of all of that stuff. So it turns out that can play a significant role in how galaxies get their stuff and form stars and turn off forming stars, and a variety of other aspects about how galaxies live their lives and evolve. So that's my main focus. Okay, so let's delve into some questions from the audience. I encourage you again, if you haven't and you have questions about whatever, feel free to ask them in the YouTube chat and we will try to get to them, whether it's specifically on Vikram's content and radio astronomy, or just general, you have some burning question about eclipses or something like that. I don't know, whatever you want, something space related, we'll try and get to. So, but yeah, the first questions definitely are related to the talk. Let's see. I like this one. What factors must be considered for the operation of radio telescopes, and what kind of place do we need to choose in order to build radio telescopes, like the DSA that you were discussing earlier, Vikram?
Yes, that's a really good question, actually. So you can probably see my Zoom background, which shows a little dish sort of over here, as well as pretty much nothing else, right? And so one of the main points is that we look for empty places. Doesn't matter if there are mountains or in deserts or whatever, they've just got to be empty. That's the first thing. We don't want there to be, or rather we want to minimize the amount of human-generated so-called radio frequency interference. That's the first thing. Now, you'll also notice mountains behind me, like these things over here. The mountains are, we actually think, somewhat important in actually shielding us from transmitters that are on the other side of the mountains. The idea being that we often look for valleys in order to actually shield us from other cities and so on. Otherwise, if you're a millimeter wave astronomer and you're trying to, for example, make pictures of black holes, you then probably actually do need to be on top of the mountain, where the amount of water vapor in the atmosphere is less, which both improves the quality of the images as well as the sensitivity of the individual telescopes. That's pretty much that. We want to try and get away from people, get to far-flung places of the world, sometimes be in mountaintops, sometimes in valleys, but yeah, the main thing is to be as far away from humanity as possible.
Related to that, so I know a lot of people have talked about the possibility in the potentially distant future of building a radio telescope on the moon or on the far side of the moon in order to get, as you say, to get away from like people generated radio signals. Would there be that much of a difference, do you think, between being on the Earth facing side of the moon versus the far side? Because you're quite a ways away from the Earth, but obviously it would be better to be on the far side, but that adds its own complications to the operation of this instrument as well. Do you think, like, do you have a good feel for, would it still be okay if you were operating a radio receiver on the near side?
Yeah, so let's see if I can quantify this. So a typical, so I think I saw another question somewhere in there about what is the strength of the radio signals before amplification.
Yes.
And a really good measure for that is a mobile phone at the moon. And so every single phone on the Earth is going to look like a signal that we see from distant space. Now, you're absolutely right. The Earth is going to subtend an angle of about, what is it now? It's about 4 by 4 times the size of the sun in the sky. It's it's still going to be relatively localized to a patch of the sky. And so it's not, you will be able to point your telescope away from it. But then one of the unfortunate things with radio telescopes is that even if you point your dish away from a source of interference, the interference can still leak in through the side, so to speak. And so one could still be affected by the Earth. Not to give further perspective, the Arecibo telescope also operated as a radar, and it was used to actually transmit radiation in order to map asteroids. And that radar could be observed at a distance by Arecibo of several light years. And so I think the conclusion is that certainly interference from the Earth would be a problem on this side of the moon. The other problem would also be the various emissions that the Earth's ionosphere and magnetosphere also put out. The Earth's magnetic field channels plasma from the sun, and that also emits radio waves, and that would also be a source of interference for a telescope at this side of the moon. Just to finish up, when another telescope at the Owens Valley is a low frequency radio telescope, which makes images of the sky all the time. Among the brightest sources in the sky is actually the moon. And the reason it's bright is reflected interference from the Earth.
Oh.
Which is pretty cool.
That is cool, but yeah, I guess that means it's quite problematic to be on the near side of the moon because there's just so much radio frequency interference.
Yeah, I'd say, I guess of course, given the choice between a telescope on Earth and on the near side of the moon, I'd probably take the one on the near side of the moon. But it's better to go to the far side.
The concern, and not to belabor the point, the concern I have with going to the far side is that by the time, like, obviously radio astronomy is important to us, but is not necessarily important to all of the governments of the world, or the corporations that might be starting to develop the moon in the reasonably near future. And so my concern is that by the time a radio telescope is built on the far side of the moon, there will already be a lot of radio frequency producing infrastructure on the far side of the moon as well, whether it be bases, whether it be satellites going up and around. And so I worry that because not everyone is 110% in radio astronomy, that by the time we get up there, it will be kind of a spoiled environment. But
so there's, I guess, I think most radio astronomy can really be done from the Earth. The main reason to go to the moon is to avoid the ionosphere and to go to incredibly low frequencies below 10 megahertz or so. And there isn't a lot of interference below 10 megahertz. I mean, there is if you listen to AM, but it's probably unlikely that we'll have an AM transmitter on the moon. And so designs that are going forward at the moment assume that all the communications will be at higher frequencies than any telescope operator.
I see. Interesting. Yeah. Do we have any predictions as to what sort of astrophysical phenomena would be observable in this range of the spectrum that isn't, I mean, do we have any instruments that have ever made a detection below 10 megahertz before because we've got the ionosphere blocking stuff?
So there's a great story actually about this, which is that so one of the founding people of radio astronomy is called Ravi, from Wheaton, Illinois. And basically, so radio astronomy started with a person called Jansky, who was at Bell Labs and had an antenna and found some mysterious noise in the sky. Ravi read about this and in his mother's backyard built a 10-meter diameter dish and then actually, from his mother's backyard, mapped out the Milky Way. He then went on to have a career in astronomy, moved to Hawaii for a while, and eventually got so sort of sick of the standard academic community that he went to a place called Tasmania, which is off the southern coast of Australia. And he went there for two reasons. One, to get away from everyone, And two, because the ionosphere above Tasmania is incredibly thin. And what he actually did was try to build these really low frequency radio telescopes. And I think it was 1986, he actually organized for the space shuttle to do a burn over Tasmania in order to make the first maps at 3 megahertz.
Whoa.
And so the cool thing then is that you actually, so he made the maps, that's all great. It didn't really see much, but what we think that we would see if we built a radio telescope on the far side of the moon to do that is effectively the aurorae of exoplanets. So plasma from stars other than the sun impacting the magnetic fields of planets in other solar systems. And we think that it's critical that these planets have magnetic fields, like the Earth, in order to protect them and protect any living creatures on them from their stars. And so the main reason why one would do a radio telescope at the far side of the moon is to study the habitability of exoplanets.
Wow. That's pretty awesome.
Pretty cool, yeah, it's cool stuff.
Huh, I'd never really considered that. I mean, when I think of aurorae, I think of the optical phenomena that we see on the Earth or with Jupiter and some of the other objects in our solar system, but not the radio component to it. That's super cool.
There's actually a program led by Jack Burns from Colorado and co-led by Greg Hallinan here at Caltech, which is called Farside, where it's a proposed array of about 200 radio receivers to do this on the far side of the moon. They're exploring concepts anyway at the moment.
That's super cool. I'm assuming it hasn't yet been funded.
No, not yet. It's in the process called the Decadal Survey of Astronomy for the next decade.
Okay, awesome. Okay, sorry, we went way down a rabbit hole there, but it was an interesting rabbit hole. Let's see. How much angular coverage per night is the 110 dish DSA expected to cover?
Great question. So the 110 dish DSA can instantaneously see the same amount as the 10 dish DSA, so about 7 by 7 degrees in the sky. But we of course cover a full swathe of the sky as the sky rotates above us. We don't steer the telescope. We can move it up and down, but not sideways. So we can move it in elevation and not azimuth. And so the idea is we move to a specific elevation and let the sky drift overhead. And in doing so, we see about 360 by 7 degrees, which is about, if I can do the math in my head, about a tenth of the total size of the sky every night.
Awesome. That's cool. Okay, here's a question for all of us, really. The Arrival is a classic film, although I know Vikram said, so just to clear up things for our audience, many of you may have seen The Arrival. I haven't actually seen The Arrival. Many of you also may have seen Arrival, which is a different film entirely. So Arrival came out in the last 5 years or so, 6 years, I think. Stars Amy Adams and is about contact with, never mind. Let me not describe it and give spoilers. It's a very good film, in my opinion. I think it's excellent. The Arrival is a film that came out in the mid-90s, I think, starring Charlie Sheen. And as Vikram says, perhaps isn't as high a quality film.
It's amusing. It's entertaining. At least I find it entertaining. Yeah, I'm not sure it's for everyone.
Okay, but the question is, what are your favorite space and space-related films? So everybody, feel free to chime in here. I'm trying to think what my favorite space-related films are.
Yeah, same.
I guess I'm going to say probably the classic that most astronomers will say, Contact. It's an excellent film, excellent acting, good plot, based on a very good book. It was written by Carl Sagan, the notable astronomer and and science communicator that many of you may know. And the science is, I'm sorry, my connection's so crummy, guys.
No, we can hear you.
Let this be a bad advertisement for Spectrum. Don't ever get Spectrum internet service. They were supposed to come fix it today, and they didn't even call me or show up. I got stood up by Spectrum. Oh, anyway. So no, Contact is accurate both scientifically, and it touches on some really relevant themes throughout astronomy and philosophical questions as well. I think it's excellent. But what are other ones that you guys have that you prefer?
Michael or Evan?
Sure. Okay. I
So,
can. Sorry. Yeah, you can go first.
okay, sure. I'll go ahead and go first. So I think this may be an interesting one to folks on the panel, but I think my top two, the first classically, well, I guess classic and that like it's a modern day classic would be Interstellar. At least for me, before the final, I don't know, 25, 30 minutes. I don't know if it was that long, but before that portion of the movie, I was just taken away by a lot of the stuff. I mean, granted, the story wasn't perfect. There are obviously some issues that go along with it, but in terms of, and even some of the scenes, like some of the calculations were off such that some things weren't actually physically possible. But in terms of like being a good watch, and if you don't pick too closely at the details, being pretty darn accurate, like it was really good. It was definitely a joy to watch. Fun fact, actually, with that, I was able to watch that at the Grauman Chinese Theater with my mom when it first came out. So that was a nice little Friday night outing for us. And then the second movie, this is the one that I think folks are probably gonna be like, 2001. Space Odyssey. Funny enough, when I watched it the first time, I thought I was watching the wrong movie. I had to kind of like exit out of it and be like, wait, was this the right thing? Because the first scene, for those who've seen it, takes forever to get through. It's kind of a slow watch. The first time I tried to watch, I fell asleep. But once I was, went through the movie again and really, I started to appreciate it a lot more. So much so that now looking at it with I don't know if I would call it more mature eyes, but at least like more understanding eyes. I think Kubrick did a fantastic job.
Absolutely. And two notes associated with both of those. One, I think we're required to say that Interstellar, the script was written by Kip Thorne, who is a professor in our department, who also was awarded the Nobel Prize a couple of years ago for the LIGO discovery of gravitational waves. But then the thing that's been in the news in the last 2 weeks associated with the discovery of this monolith in Canyonlands National Park that's very similar to the monolith that's shown. I think
weren't you there a month or two ago?
I was there, but I was not the person responsible for that.
Are you sure?
I think I was about 15 miles away from that particular location. I didn't go to the Needles district, but I wish I had. That seems like it'd be a pretty cool discovery to see this metal monolith in the middle of Canyonlands in the middle of nowhere. So anyway, Michael, what do you think? What are your opinions on this?
Yeah, Evan, you stole my answer.
Sorry.
2001 Space Odyssey is awesome. I read the book like a long time ago when I was 13 or something. I watched the movie a few years later. I have to say I like the book better than the movie, especially the ending. I think the book's ending is like less confusing, a bit less mystical, I would say. But yeah, both are really good. Okay, so I'm going to give a different answer, which is something I just started watching. Star Trek is obviously a classic. Everybody's heard of it. But I've actually never seen a single episode before this year, before the lockdown began.
Wow.
So when the lockdown began, I went to Amazon Prime because I have it already. And I was like, what can I watch? And I was surprised that I could watch all 3 seasons of the original Star Trek. So I just started binge watching. So I finished season 1 very quickly. I'm halfway through season 2. And yeah, I should be finished, the first 3 seasons. And the thing that I really like about Star Trek is that it's very optimistic. It's a vision of the future where humanity comes together. It's a peaceful, harmonious, prosperous society. It's not like a post-apocalyptic environment, but we have like faster than light spaceships. We travel the galaxy. We discover all sorts of weird and interesting and unique things. And we interact with dozens and dozens of alien species in a very, often a very productive and very peaceful way. Sometimes not, sometimes there's war, but, I think that's expected. Yeah, so if you look at a lot of the science fiction today, it's really pessimistic. There's a lot of apocalyptic literature and film. There's a lot of fear and anxiety about the future of technology. Some of that is well justified, but I think we need some optimism in our lives because technology is not all bad. I will venture to say that most of us watching would not be here if not for technology. We would have died in infancy, or we would have died at age 20 due to an easily preventable disease. So yeah, I really like the optimism and the vision of Star Trek.
Absolutely. I kind of wanted to add a little something too for two other shows, or really just two other things, I guess. The first is that there's another show on Amazon Prime that also does a really good job with sci-fi, and that's The Expanse. I think someone mentioned it in the chat, but it's a fantastic show. What I like about it too is that admittedly, it's been a while since I've seen. I haven't watched the past the 2 seasons, so I'm still trying to catch up. But the direction of the show was going what I thought was a very realistic approach to it, and it sort of gets at what I would deem some of the realities of the situation. So in some cases, of course, it's very pessimistic, right? So it's at odds with what we would want to watch, as you were kind of mentioning, Michael. But a lot of those things that are being mentioned in the show are things that we as humans care about. And I've always kind of liked to see hard sci-fi mix with us humans and how we actually go about living with the world. The second thing that I wanted to recommend, or that I really, really enjoyed, I could not put this book down, was A Rendezvous with Rama. So this was a good book by Arthur C. Clarke. And for me, I usually don't find books that are page turners for me, but this was one of those where I had to deliberately stop myself from reading until 3 a.m. because that had happened too many nights in a row. And I was like, okay, and I'm a slow reader too. So you're probably like, how can you just couldn't finish the book in the first week? I'm a slow reader, so it still took a while. But what's cool with that, I haven't watched the sequels, I haven't read the sequels, and those get a little bit more into like the humanity aspect of it. But the first one, in terms of just being very hard sci-fi, was just fantastic. And it really helps you like sort of dive into the mind of like what it would be to come across the remnants of some other civilization, and how cool that would be. So yeah, definitely would recommend that. Rendezvous with
That's
Rama.
my second favorite book.
Nice.
Wow.
It's so good.
I've got to read this.
So it's worth it. Totally. Strongly recommend.
So Vikram, what are your opinions on films?
Well, I mentioned a few. Let's see. I don't know. I really like The Dish. I think The Dish is awesome. So, it's just like sit back and watch them sort of, bumble about and point the telescope. It's great. It's almost a true story as well. Let's see. Other ones. I think what else is a good astronomy movie? So one time, one of the professors in the department hosted a radio astronomy movie marathon. Let me try and remember what we went through. We went through definitely The Dish. We went through Contact, The Arrival, and the fourth, which is what I used to jog my memory, and which I think is probably my favorite astronomy movie of all time, is, I'm sure you could guess, GoldenEye.
Oh yes. James Bond film from 1996 starring maybe 92, Pierce Brosnan.
96. It was like, I remember it was the first movie I ever saw in the movies in 96 or 7. I forget exactly when, but yeah.
Right.
Yeah.
It features the Arecibo radio telescope.
It was prophetic even, I guess.
Oh, okay, I see. Because in my head I was like, GoldenEye, isn't that a 007 movie? Okay, I see. It exists.
It heavily features Arecibo at the end.
That's cool.
Yeah, I think that's my favorite modern Bond.
Yeah.
Nice. When was the dish released, by the way?
I think it was, if I remember correctly, 2001 or 2002.
Oh, okay.
Yeah.
Gotcha. Missed my radar.
Okay, thank you guys for your opinions. Very good topics there. Very good films, and I'll definitely have to check out Rendezvous with Rama. I've heard of it, but I've never read it. So, all right. This is a question for Evan Nunez. Can you talk about the development of 26 aluminum and other radioactive isotopes that could heat planets? And how those radioactive isotopes form or change in galaxies over time.
Mm-hmm. Yeah, so this is a really good question. And I unfortunately won't be able to give you an answer that's specific to radioactive isotopes, but I can at least give the, like aluminum 26, but I can at least give you a big picture of how effectively how metals are formed in the universe. So I think we've all have heard of this, that very early on in the universe, you had a huge amounts of hydrogen, some amount of helium, and the trace amounts of metal. And so the three channels that we know of to get heavier elements are basically these three. The first is fusion inside of stars. The second is fusion from the explosion of those stars, and then fusion during the explosion of star systems. And then the final is actually some nucleosynthesis at the very early parts of the universe. And so what you end up needing is a specific density and temperature and environment such that you can seed and use lighter elements and then effectively convert those into heavier elements. And the place that we know of that this happens is in the cores of stars, both low mass and high mass, as well as once stars gets to the end of their lives and when they explode. And so this can be in explosions like core collapse supernovae, which is where you have a very massive star at the end of its life, where it fuses all the way up from, fuses elements all the way from hydrogen to helium, and then they have different phases like to carbon and nitrogen, to silicon, and then finally up to iron. And once you get to iron in the core, you start to get endothermic reactions. So you basically have a collapse. When you have a star, you basically have a competition between two forces: the radiative pressure pushing outwards from the actual fusion themselves, and then gravity pushing inwards. And so once you have that balance, we call that hydrostatic equilibrium. And once you start to fuse iron, you no longer get any repulsion anymore from the core. So you just get a collapse. And depending on how dense the core is and what have you, you can actually get a bounce back from all that material crashing into the core. Bam, now you have yourself a core collapse supernovae. Now, what that does is it liberates all the material that had been, well, not all of it, but the material that had been fusing outwards in different shells, that goes out into the medium. And then depending on the explosion and the temperature and the mass and everything, you can also have fusion during the explosion. So this is called explosive nucleosynthesis. This is very, very high temperatures. And a lot of that, in part of the of that explosive nucleosynthesis, where you can start to get other elements that are radioactive, if I'm remembering correctly. Well, I mean, actually, each of these steps you could get that, but in particular during that part. And then the other places too that you can see this in terms of explosions would be like the mergers of neutron stars, or when a white dwarf, which is another stellar remnant. Uh, um, well, I guess to keep it simple, once it accretes enough mass, although there's a more complicated explanation to that, then it also could explode. And those are called, so that's actually a different type of explosion, say thermonuclear explosion. But nonetheless, all of that to say that very early on in the universe, we had basically just massive stars were the first alchemists, as I like to think about, the first places where heavy elements were produced. And then from there, the metals that they then liberated and injected into the medium then formed the next generation of stars, population 2, and so on and so forth. And now here we are. And then of course, intermingled within, that big jump in time that I just mentioned, then you have the production of radioactive elements that then of course get seeded and helped form and now heat the different cores of planets. So yeah.
Excellent. A very wide covering response, going through supernova reactions and core collapse and all of that. Excellent. Excellent. And a related question, follow-up question, I think from Michael, who does more exoplanet research, is how important are this quantity of radioisotopes in the cores of planets for maintaining the magnetic field or other impacts like holding on to the atmosphere, these sorts of things. So do those radioactive isotopes play a major role in kind of defining the evolution of a planet or making it habitable?
Mm-hmm. Yeah, it definitely does. So the reason for that is the whole reason that the Earth has a molten interior right now is because it has radioisotopes. The radioisotopes decay. The decay products have energy. That energy gets converted to heat, and that maintains an internal heat source that prevents the planet from cooling. So there's a really interesting anecdote about this. One of the first scientific attempts to estimate the age of the Earth was by Lord Kelvin. If you're taking any physics, he's the same Kelvin that the temperature scale is named after. So when you say something is like X Kelvin, that's the guy. So he did a lot of pioneering work in thermodynamics. So he assumed that the Earth started out as a molten bottle rock, and he calculated how long would it take for the Earth to reach the present temperature from that molten bottle rock. And his answer was from 20 to 400 million years. Now the true answer is 4.6 billion years, so he was way off. And then he did another calculation, which is if you take the sun and you assume that it was powered by gravitational collapse, how long would it take for the sun to burn out? And he got 20 million years. So he was like, okay, these two answers are consistent. The Earth must be around 20 million years old. And it was actually the geologists and the biologists who said, no way. Because the geologists could see all of the layers of rock that got like deposited over hundreds of millions of years. And they had no real way of estimating the age of these rocks, but they could tell it had to be more than 20 million years. And the biologists, this was after Darwin's theory of evolution. So they knew about they knew about the huge variety of life on Earth, and they knew about the slow rate of change from generation to generation. So they had an intuition that 20 million years just wasn't enough to get out of the biodiversity that we have right now. So, okay, the reason that he was wrong in these calculations, well, for the Earth, is that he didn't know about radioactivity. Once you take into account radioactivity, the answer goes from 20 to 400 million years to 4.6 billion years, which is a huge increase. And for the sun, he didn't know about nuclear fusion. So once people knew about nuclear fusion, they could properly estimate the age of the sun, which is around 10 billion years. Well, right now it's around 5 billion, but it's going to last around 10 billion years. So if you don't have a molten interior, you don't have a magnetic field. And if you don't have a magnetic field, then the radiation of the sun and something called the solar wind, which is like particles that come from the sun, they become much more effective in stripping the atmosphere. So in this way, in only a few 100 million years, the sun will blow off the Earth's atmosphere, and then it wouldn't be habitable anymore. This is what happened on Mars. We think that Mars, when it was young, used to have an atmosphere. It used to have oceans and lakes and rivers. It used to be very Earth-like, right? But Mars is much smaller than the Earth is, so it cools a lot faster. So it cooled, the interior became solid, the magnetic field went away, and it lost its atmosphere. And now, if you look at Mars, there's no water whatsoever. There's ice, there's like some water beneath the surface, but there's no surface water because there's no atmosphere. And when you have no atmosphere, water just sublimates. It turns into gas instantaneously. Yeah, so very important.
Yeah, that's super important. I have a couple of follow-ups that are related to all of this, and that is, one, do we know the strength of other planetary magnetic field? I mean, obviously in the solar system, yes, we have ways of figuring that out. But for exoplanets, other than things like what Vikram was talking about, where potentially we could observe the aurorae using very low frequency radio observations, do we have any kind of indications of what the magnetic fields of exoplanets are?
Nope. Yeah, so this actually ties in very well with what Vikram was saying. Measuring the planetary magnetic fields has been, a very important area of research that hasn't so far yielded any results. And the reason is that one of the, easiest ways of measuring an exoplanet magnetic field is to detect the radio emission from that exoplanet. Lots of people have looked. There's been no definitive detections. Although just today, I saw a paper on arXiv that claimed to detect radio emission from Proxima Centauri b. I read the abstract, but I haven't actually read the paper. So I'm curious about whether Vikram has any opinions.
Michael, is this the LOFAR result from Philippe Zarka's group?
I think so. So they monitor Proxima Centauri b for like 1.5 days, like one and a half orbital periods. Yeah. And they say that like the intensity and the polarization of the signal is consistent coming from the planet.
Yeah, so I've been aware of this for a little while, and also aware that follow-up observations didn't show all that much. Yeah, I think it's very much it's definitely a very promising result, and that group is actually building something called Nenuphar, which should do this properly when it's fully built. But yeah, it's Philippe Zarka is sort of one of the real founding fathers of this field, and yeah, it's one of these cases where it was too interesting a signal not to publish, I guess is what I'd say. Yeah, in general, I think that, I guess maybe a question for you, Michael, is like, are there no Zeeman splitting lines that can be used?
Zeeman splitting lines. So this wouldn't be radio, right? This would be like optical, infrared. Right. Yeah, so I've actually heard one proposal from actually a graduate student who used to be at Caltech, Antonia Lepkich.
Yeah, Antonia. Oh, yeah. That's cool. Yeah.
I'm sure I messed up her last name.
Yeah.
Yeah. Okay. So
I think.
Yeah.
Say
She's
that again.
now faculty in the Netherlands.
That's right.
Yeah. So she pioneered a new way of observing exoplanet atmospheres, and it's the way that I'm using right now, which is when you have an exoplanet atmosphere that's escaping due to stellar irradiation. The main component of that escaping atmosphere is hydrogen. But the problem is, to observe hydrogen, you need to go to space because you need to look in the ultraviolet, and Earth's atmosphere blocks ultraviolet. But the second biggest component of the escape is helium. The helium absorption signal is at 1.083 microns, and it turns out that that's visible from the ground. And that's important because we have much bigger ground telescopes than we have space telescopes. And also, it's much easier to get time on the ground telescopes, especially if you are at Caltech. Yeah, we have really good ground telescopes.
Very true.
Yeah, so I think she published a paper where she proposed using instruments that can measure polarization in addition to intensity. And if you measure the polarization of this outflow, in some way you can back out the planetary magnetic field. And I think she said that it was marginally detectable, even with current generation instruments, although I might be misremembering that part.
Yeah, that's fascinating. I'll look that up. That's really cool.
And one more related question to all of this, since I think it's pretty interesting and might be interesting to our audience. There's a lot of talk, especially with SpaceX, about the possibility of terraforming other planets. I don't necessarily agree with all of this, but there are ethical issues associated with this. But scientifically, what you're describing, if we wanted to make Mars more like the Earth, so it was more habitable to humans or life, at least the kind of life that we're accustomed to, it seems like it would be extremely difficult because we'd have to give it a magnetic field that would make it so the atmosphere was more likely to stick around instead of being ablated and knocked away by the solar wind particles. It seems like it would be extremely challenging to give a planet its own magnetic field if it didn't already have a magnetic field by itself. So are the ideas of trying to terraform an object like Mars or the moon or anything that currently lacks a magnetic field just totally impossible?
Actually, I think for Mars, that's not really a big problem. Because the time scale for atmospheric mass loss is millions of years. Maybe it's even hundreds of millions of years. I forgot the exact number. But even if it's only a million years, for any realistic terraforming proposal, we're going to give Mars an atmosphere in 100 years or 1,000 years. And that's like 1,000 times less than the mass loss time scale. So yeah, we'll give Mars an atmosphere, and we had to replenish it, but we only had to replenish it at maybe 0.01% of the rate that we initially used to give Mars an atmosphere in the first place. But the biggest hurdle is that we just don't have the economic capability to do this. I read an estimate somewhere a long time ago that if you take the GDP of all of the countries in the world right now, and you convert all of that to terraforming Mars, then it will take thousands of years. Yeah, so first of all, you can't take all of the GDP of all of the countries in the world, right? We had to make food and shelter and lots of other stuff. And second of all, nobody's willing to wait thousands of years. So yeah, until we become a truly interplanetary species with a GDP that's tens of thousands of times higher, then there's no hope.
Or we make the technology cheaper to go and replenish or generate an atmosphere there. But yes, it's a long ways off. Okay. Yes. Okay.
And also, it's a very structured process. So if you already have a Mars colony there, they can't live there. You had to be basically creating large-scale natural disasters on Mars, like every single day, in order for terraforming to happen within even thousands of years. So if there's already a habitation there, which is likely going to happen before we're capable of terraforming, then you have to evacuate them. Yeah.
I see. Okay. Interesting topics. All right. Lots more questions. Vikram, how much of the radio spectrum does the solar wind obscure? And is there anything observable from beyond our heliopause, beyond the extent of our solar wind and solar magnetic field, that's not observable from within the solar influence? I think specifically the radio part of the spectrum, but yeah.
Yeah, that's a really interesting question. The short answer to that is not a lot. The solar wind, by the time it gets to the Earth, is relatively diffuse and in fact, is diffuse enough that we can actually observe radio sources within about 10 degrees or so of the sun. The biggest problem with observing close to the sun is actually that the sun itself is a bright radio source, and so it interferes with the observations. But the solar wind is just diffuse enough that it doesn't affect us too much. We actually, in the early 60s, people were very interested in using the solar wind and the effects of the solar wind on distant radio sources to actually measure the sizes of those sources. Because as all of you will know from looking up the night sky, stars twinkle, but planets do not. The bigger an object is, the less it twinkles. And radio sources twinkle in the solar wind at frequencies of a few hundred megahertz and below. A large array was built in the UK to actually detect this twinkling and use the extent of the twinkling to actually figure out how big radio sources were, because that was a big problem. How big were these strange sources of radio waves in the sky? And that very array was the one that Jocelyn Bell Burnell used to discover pulsars. And sort of past that discovery, I feel that the field of sort of interplanetary scintillation has steadily sort of declined since then, as we've gotten better angular resolution and so on. But it's undergoing a bit of a resurgence now as well. But yeah, that's pretty much the main effect.
Okay, thank you. This is a question for Vikram, but I think we could all potentially chime in. One of your slides in your presentation seemed to imply that most observational astronomy, perhaps as the name suggests, is focused on visible matter, stuff that's actively giving off light, right? Or scattering of light. But as you pointed out, that's the minority, that's a very small percentage of the total amount of stuff in the universe, because it doesn't include dark matter or dark energy. What are ways of studying those non-visible components, those invisible components like dark matter and dark energy?
Yeah, and maybe I can address a few of the other questions as well that were on a similar topic. I think there was one that asked, why can't we observe the hot matter in infrared, and so on. And so, yeah, the main thing, so first of all, if we just take the normal matter, what astronomers call baryons, what I've said is that something like, if you sort of take 1 divided by 5, about 20% of it is visible, so to speak, that it gives off light, and the rest does not. Why doesn't it, even though it's so hot? It's because it's too hot and too diffuse. It's well over 1 million degrees Kelvin, and in basically the only way that it can emit light is in the X-ray band. And unfortunately, the amount of radiation that it emits actually goes as the square of the density of the gas, not just as a density, but as a square of the density. And because it's so diffuse, it's really difficult to see this except in sort of the densest galaxy clusters and perhaps in the halos of some galaxies. It's mostly invisible to at least our current telescopes. I'll let other people speak to both that and dark matter and dark energy and stop there, unless I go on too long.
So to summarize your point, though, this stuff is so low density and spread out and so hot that it's just not able to be seen with our current technology.
Absolutely.
Okay. Who wants to handle dark matter and dark energy, guys? I can try too, but spread the love. Spread the love. All right, I'll talk a little bit. So dark matter and dark energy, we can't see them directly. Obviously, that's why they're dark. For dark matter, there are a few different ways in which we can infer the presence of it to try and figure out what it's doing or where it is. The way that it does interact with other matter is gravitationally. So dark matter, even though a clump, we'll just say there's a clump of dark matter in my hand, I might not be able to see it because it's not interacting with light or with the electromagnetic force, but it still interacts gravitationally with the objects around it, which is how we have kind of figured out that it needs to be present in order for our models of the universe to operate correctly. And so one way that we can study it is by looking for its influence on what we can see. In galaxies, for instance, we can see how quickly a galaxy might be rotating or moving, which indicates how much gravitational mass must be present in order to allow it to do that. And so that can tell us something. There's also research in the cores of, that's focused on the cores of dwarf galaxies. So these are low-ish mass galaxies that are much lower mass than our own Milky Way galaxy. And it turns out in the cores of those galaxies, you get very, very high densities of material, of mass. And it's thought that potentially that puts constraints on whether or not dark matter, while it doesn't necessarily interact with normal matter, like protons and electrons and neutrons and such, it might interact with itself and potentially scatter off of each other or self-annihilate. And when it self-annihilates, create some sort of electromagnetic signal, like an explosion, something like that. So that's a very dense environment where you have a lot of dark matter that's crammed together very closely. So if you were going to see some sort of interaction where a dark matter particle running into another dark matter particle might have an observable effect, that would be the environment in which to look. And so that's a place that there's active research going on to the nature of dark matter. There are dark matter direct detection experiments that are going on the Earth. One that I know of is called Xenon, Xenon, which is in a mine in Italy. And that, as the name suggests, has a very large vat of xenon, which is a, let's see, isn't xenon a noble gas? I think xenon's a noble gas.
Yeah.
Mm-hmm.
So it has a very large chamber filled with this stuff. And because it's a noble gas, it means that it's not very chemically active and reactive with itself or with other elements. So it isn't expected to have any kind of spontaneous interactions, but now I have to remember the details. Perhaps you guys can fill in where I'm missing gaps, but I forget the details of the xenon experiment or experiments like it, but I thought the idea was to just sit there and observe it. And if a weakly interacting massive particle, a dark matter candidate, were to travel through that, it would cause, or it's predicted that it could cause, a spontaneous reaction that would be visible from these photodetectors that are constantly observing it. But I forget the exact interaction detail.
I forget the exact interaction as well. I think you're absolutely right. The main point is just to get mass within the detector, and that too mass that doesn't emit anything by itself, and preferably mass that's relatively transparent as well to the photodetectors. So yeah, I think that's pretty much. I don't remember the details. And
it's done in a mine. The reason it's done deep underground is to avoid any kind of other, like solar wind or any atmospheric phenomena that might cause a similar reaction, because you have all this rock in between you and the detector that it would presumably block that stuff, but it wouldn't block these weakly interactive massive particles necessarily. So
the problem of what dark matter is probably one of the more embarrassing aspects of being an astronomer. For a long time, at least in the early to mid 2000s, there was a strong suspicion that these weakly interacting massive particles, or WIMPs, were the correct dark matter model. But as the limits from these sort of detectors further down, we're now as puzzled as we ever were, such that the range of possible dark matter particle masses spans about 92 orders of magnitude. Yeah, 92 orders of magnitude. I'll say it again. And so to put it in perspective, one of the models is that these particles are so light and so sort of small that their effective quantum wavelengths are on the scales of galaxies. And that's considered a leading model to actually suppress the formation of small galaxies and sort of cuspy structures in the middle of galaxies. The idea is that the central part of the galaxy, like the Milky Way, would be a Bose-Einstein condensate of these particles. And so you effectively get a flat density profile in the inner parts of galaxies and suppress the formation of small dwarf galaxies. That's one end of the spectrum. The other end of the spectrum are black holes of a few tens of solar masses. So the one sort of leading model for dark matter is that the universe is just full of these sort of order 10 solar mass black holes, like those that the LIGO has been finding.
Yeah, so a common question that people have when they hear about dark matter is, how do you know it's not just some dark gas that you haven't discovered yet, right? Like, you tell me about like all of these measurements that indicate there must be more mass in the universe than you can detect. Maybe you're just not very good at detecting that. We actually know that's not the case from the cosmic microwave background. So this is the radiation that's emitted when the universe was a baby, when it was only 300,000 years old, and it was at a temperature of 5,000 degrees. So it was glowing red hot. So at the time, the universe was a uniform gas that emitted visible light, but the visible light has since redshifted, meaning its frequency has changed, so that it's now microwaves, which is why we call it the cosmic microwave background. But anyways, in this early era of the universe, there were sound waves that propagated through the universe and changed the density of the universe at different scales. And it turns out that normal matter interacts with the sound waves in a different way than dark matter, essentially because normal matter has gravity and pressure, but dark matter only has gravity and no pressure. So if you look at a plot of the cosmic microwave background power spectrum, you see like lots of bumps and wiggles. And the ratio of two of those peaks tells you the ratio between the amount of dark matter in the universe and the amount of normal matter. Normal matter being everything that's made out of atoms. So everything that we can, everything that we know of, all of the particles that are explained by our current theories of physics, those fall under the rubric of baryonic matter. And we know that that's far from enough from explaining to explain the cosmic microwave background.
Right. Yeah, I mean, honestly, I think you guys said it right. It's an embarrassment that we don't necessarily understand the nature of dark matter. But on the other hand, like a lot of people are like, why do you believe in this invisible stuff? And it's like, look, we don't want to have to believe in it. We aren't just like,
visible.
Yeah, we are. There are various pieces of evidence that point towards nothing else. We have tried all of these other ways, like to get rid of dark matter, but we can't get rid of dark matter. We have to invoke this unseen gravitational mass component. And I wish that we couldn't. I wish that we could avoid it, but we've tried everything else, and there's just nothing else that fits the bill, unfortunately.
And actually, just to add on to a few more things that we've already mentioned in terms of like more evidence for dark matter. Actually, maybe we did mention this and I zoned out, but one of the key drivers for dark matter becoming an accepted theory was looking at galaxy rotation curve. So this was spearheaded by Vera Rubin. There's an observatory that's going to be named in her honor, where you would expect, if you have all the mass of some object concentrated at the center, like let's say the solar system, that as you move outward in radius, that you should see a decline in the velocity of those objects. So in other words, Mercury moves very, very quickly around the sun as it orbits, whereas let's say Neptune, which is at the outer part of the solar system, goes very slowly, right? And so that's what you expect is a decline. What we end up finding though is that when you plot the rotation curves of galaxies, this is looking at velocity and radius, you end up finding that for a little while it kind of looks like it's going to follow what we would expect, and then it just sort of becomes constant. And what that would point to, assuming that you've accounted for all of the mass you could with light, you would still have this residual mass left over. So it's like, well, there has to be something else that's basically lifting up and keeping the velocity constant, even though we know that it should be dipping below. And actually, I mean, there's a sort of a simple equation that you can take a look at to see why this would have to be the case. But that was one point of evidence. The other thing too is if you were to look at the how hot galaxy clusters are, and what that would infer about the mass that you would need in order to make the gas that hot, it turns out that you would need, again, a lot more mass to explain this away. And what's interesting too is that all of these lines of evidence that we are mentioning, in terms of the quantity that you would expect of dark matter, they're all somewhat comparable. So this is, again, another one of those things where we look at it and we're like, huh, we have completely different realms of astrophysics that are all pointing to the same thing. And just kind of echoing what Cameron says, we really wish this wasn't the case, because this is the majority of the universe. But here we are. And so I said all that to say that, yeah, this, just kind of belabor the point that Cameron's making, this isn't just in our heads, and we aren't just, wanting this new thing to happen, because what this really signifies is that we just don't know, right? And of course that's fun for us, because that's the fun is learning more. But that's a lot to not know, So
absolutely. Yeah, the ratio of dark matter to normal matter in the universe is 4:1. So it's not like there's some tiny effect that we can barely measure, and it might be there, it might not be there. No, this is the thing that dominates the gravity of the universe, and always has and always will.
Indeed. Well said. I'm going to pass on discussing dark energy for this time and move on to another question.
Yeah.
It'll be more bumbling, but because we know even less about dark energy than we do dark matter. But anyway, there's still more questions to address, and we've only got like 12, 13 minutes left. So, well, I guess a really quick one that's more practical, I guess. What are the best universities for studying computational astrophysics? There are lots of good institutions that have strong computational astrophysics programs. Caltech is one. Princeton is very good. Generally, computational departments go hand in hand with departments that are strong in theory. But honestly, I would say the best computational astrophysics program for you, if you're looking to go to graduate school, would be one that you can get into, because otherwise it's probably a moot point. But honestly, there are lots of good programs. I think just off the top of my head, the highlights are Caltech, Princeton, Stanford, Harvard in the US.
Columbia for the Flatiron.
Say it again.
Columbia or NYU for Flatiron.
Yes, that would be, yeah, Columbia and NYU. University of Illinois Urbana-Champaign is excellent. They have a strong computational just program in general. Similarly, what's the school in Pittsburgh?
Carnegie Mellon, you mean, or University of Pittsburgh?
What was the first one you said?
You mean Carnegie Mellon or?
Yes, Carnegie Mellon.
Yeah.
I mean, just because they're an incredibly strong computational department in general. Berkeley, very strong. I guess
we can keep going. There's a lot to.
Yeah, there's a lot of. There are a lot of good programs. Okay, so moving on. Let's see. how does the formation of magnetars differ from that of regular neutron stars? You talked about that magnetars, at least in this instance that you discovered, or that Chris Bohenek, your student, discovered in our own Milky Way, was this origin of the fast radio burst. But why would you get a magnetar from the evolution of a star rather than just a plain old neutron star?
Plain old neutron star, great. So short answer is we don't know. We think that there's, for every neutron star or normal neutron star that's out there, we think there's something like 2, maybe 3, sort of maybe a factor of 2 or 3 less magnetars. Like for 10 neutron stars, there'll be 2 magnetars. We think, and we know from where they're found in the Milky Way, that they're formed in massive stellar supernovae. We don't know what is special about these supernovae yet. We also can think of several other ways to form magnetars. For example, from the merger of 2 neutron stars, from the merger of 2 white dwarfs, from the merger of a neutron star with the core of a massive star, from the accretion-induced collapse of a white dwarf, where it's accreting matter from its replicant companion and then it collapses to a magnetar. These are all ways of forming magnetars. The rates of all of these types of events are incredibly poorly constrained to an order of magnitude at best. And so short answer is, yeah, we don't have a great idea about what makes the formation of magnetars special relative to the formation of normal neutron stars. We just don't know.
Okay, that's, yeah. I wondered that question as well, so this is informative for me too. Thank you. Here's a question that we had prior to the lecture. What will radio astronomers use now that Arecibo has collapsed? Like what special function did Arecibo serve in the radio telescope community that no other object may possess?
Yeah, that's a really interesting question. So I think one of I mean, of course, the key thing with Arecibo is its size, right? It was just really big and really sensitive. Some of you will know about a telescope called FAST, or the 500-meter aperture spherical telescope in China. It is bigger than Arecibo and more sensitive than Arecibo, and so it fulfills some of the functions that Arecibo fulfilled, especially for the observations of some pulsars and hydrogen gas in the Milky Way and beyond. Some of the special things that Arecibo did, one was planetary radar, and so the idea of imaging and tracking near-Earth asteroids, as well as some more distant asteroids, as well as some planets as well. The planetary radar system in Arecibo was the most sensitive system. Some of its functionality may be replaced by Goldstone, but not with the same level of sensitivity. Arecibo provided the best ephemerides for potentially hazardous asteroids. So that function will have to be replaced in some way. One option is to go to higher frequencies. Another option is to go to large arrays of telescopes like those that I was talking about. In the US itself, and for the US astronomical community in particular, we're hoping that the DSA 2000 array that I talked about will take on a lot of the pulsar timing and a lot of the hydrogen observations that Arecibo was doing, as well as potentially things like the so-called next generation very large array, and maybe even the square kilometer array in South Africa and Australia. So yeah, Arecibo was very special and did a lot of amazing things and still has been doing a lot of amazing things. I think there were 2 separate, so I think there was about $12 million of instrumentation development ongoing for Arecibo, currently funded, which gives you a sense of how useful it's still seen as by the astronomical community.
Yeah, even though it was almost 60 years old.
Yeah,
right?
yeah, $12 million of instrumentation development, and these, to build cutting-edge instruments to take it, to the next, to push the observations even further.
For the radar that it was doing, it was always my understanding that it was the and you mentioned this in your talk, that it was the transmitter. So it would transmit a signal that would then bounce off of solar system objects like, near Earth objects or whatnot. And then there was another location that would get that radar back. But was there some way it could operate and do radar just unto itself without an auxiliary receiver?
Yeah, it did. So it would do both. The idea would be that you transmit, and then you stop transmitting just when the receiving is expected to have to commence, like after it bounces back. And you turn off your transmitter, turn on the receiver, and then record the data. And so the so-called monostatic radar was, a really big part of what Arecibo did. Bistatic radar, where you have one transmitter and one separate receiver, is sort of a slightly newer thing, and it's been pioneered by various people like Jean-Luc Margot at UCLA. Mike Bush was a graduate student here at Caltech who actually used a very long baseline array in the US, the very long baseline array, as a radar receiver to actually map the motion of the radar signal across the Earth in order to extract more information from it, such as the spin of various asteroids. Yeah, Arecibo, but of course, the transmission function was really the big thing, but I mean, having sensitivity to receive was no less important.
Okay. And FAST, the Chinese kind of similar aperture radio telescope, isn't capable of doing transmission. Is that correct?
Yeah, they're not equipped with a transmitter. I'm not fully aware of the engineering considerations here, but one of the big differences between FAST and Arecibo is the way that the platform is suspended. FAST's platform is much lighter and suspended in much lighter cables, and they have a very sophisticated system to actually keep it in place and stop it sort of jiggling around in the wind. The system obviously works, but my understanding was that it's difficult to actually place a really heavy transmitter in the platform.
I see. Interesting. Okay. Okay. We only have a couple minutes left, but one follow-up to kind of our group question before, which was what are our most recommended or favorite science fiction films, is what are our least favorite science fiction films and why? So what kind of space-related movie have you seen that you just detested, and why was it? And I'm gonna maybe say something controversial. If it's more than 10 years old, I think you can say a spoiler associated with it, maybe. Because I feel like 10 years is kind of the expiration date on a film, especially if this is a bad film that people may not want to see anyway. So anyway, do you guys have any good ones that you really just...
I didn't like First Man very much.
Oh, okay.
Yeah, I didn't like it.
I haven't seen it.
Yeah, I wouldn't personally. I don't know. I didn't like it. It just somehow it just wasn't. It didn't feel anywhere near a realistic depiction, a realistic biopic, which I felt like it was meant to be. It just, for example, they would sort of cut in real audio at times, and the voice would be completely different. I didn't appreciate it that much.
Okay, that's fair. What about you guys? Evan, Michael?
I think for me, the two movies that come to mind, it actually just got dropped in the chat, Star Wars. Now, I do want to note that I'm actually a Star Wars fan, so I do enjoy the movies. for what they are. I don't know. Hopefully I don't offend anyone with this next thing, but to me, they feel like kids movies, to be honest. Like, it's a good watch, at least for me. I never found anything too deep about them.
Cuts to the core. I love Star Wars.
I don't know. It's whatever. But in terms of like the actual like science of the movies, it's just nothing in there is just physically possible. So for me, the step is to get past that. And once I do get past that, I enjoy them. The second movie that I can think of is The Core. If anybody ever remembers.
Oh, that was terrible. It was really
bad. So bad. Nothing in it was convincing.
That was awful.
So for those unfamiliar, this is I'm already kind of sketchy on the details, but either way, there's like some scientific mission in this movie that's trying to get to the core. There's probably some other plot point that I'm forgetting, but either way, I just remember being so appalled by the entire movie that I was like, yo, this is all bad. So for me, those are my top two. Although I would recommend watching Star Wars, I would not recommend watching The Core.
Yeah.
Yeah, my when I was in grade 9, my science teacher showed that movie to the class, not to point out what's wrong with it, just as a scientific educational film, because I don't know what happened. I think he was sick that day or something. Yeah, so that's
The Core, Michael.
Yeah, The Core. So I saw it as a educational
That's
film in science class. Grade 9. Okay, let's see. What movie how about Plan 9 from Outer Space?
Ooh, that's a good one.
Yeah, exactly. That's actually something you should watch, because it's good. It's so bad that it's good. And it's one of the movies that everybody agrees is so bad that it's good.
Yeah, most people consider it to be like the worst film ever made.
Yeah, exactly. Wow. How often do you get to watch the worst film ever made? Very often. Yeah. It's from 1959, and the special effects are bad, even for 1959. I think at one time you can see the shadow of the microphone boom. And the dialogue wasn't convincing at all. The aliens looked exactly like humans, and I mean exactly. Not even Star Trek aliens. What else was bad? Yeah, I forgot the details, but you should go watch it.
So what's fresh in my mind is because I watched it last weekend. I watched Ad Astra. I really didn't care for Ad Astra, even though it came out in the last year or so. It's a Brad Pitt film about 100 years or so in the future, maybe. Yeah, I wasn't a big fan of that. But I'd say if I'm thinking about worst space-related film, yeah, The Core is up there. Event Horizon. Have you guys seen this movie, Event Horizon? Yeah, don't. It's like a horror movie in space where somehow they have a black hole that somehow through magical physics is supposed to be powering their spaceship. They're somehow using it, and somehow it starts bringing in monsters and people from the past and the undead. It takes itself very seriously, and it's bad. It's bad. So I think that's probably my least favorite science fiction. But anyway, well, we're at 9:03. And there's still a handful of questions, but I think we should probably retire. Thank you very much, Vikram Ravi, our speaker for tonight. Excellent presentation and way to address lots of different realms of astronomy and physics in your questions and in your presentation. And I hope DSA 2000 gets funded in the future. Super exciting. I encourage people, if they are in California, to go check out the Owens Valley Radio Observatory. Although not right now, during the pandemic, I think it's closed to visitors. But
yeah, it's closed to visitors right now. But we'll post notices on our website as soon as it's open again.
Yeah, it's a cool place, both for the science that's being done there as well as just the natural environment. You're right next to the Sierra mountain range. You're right next to Death Valley. And the town of Bishop is super cool. It's just
it's awesome. It's a really great place to spend time.
Yeah. And thank you to our panelists, Michael Zhang and Evan Nunez. You guys did great. And thank you to our audience for attending. Keep in mind, again, these are monthly events. Our next one will be probably early January, and we'll continue to have them in perpetuity as far as I'm concerned. And then we have our Astronomy on Tap events that are occurring once a month as well. Our next one is in 10 days on December 14th. And if you have the opportunity, go check out the Geminids meteor shower that's peaking around then as well. Try and get to a dark sky location and just look up in the sky with a blanket and maybe a chair and enjoy the meteor shower, hopefully. Yeah, I think that's it for now. So have a wonderful weekend, and we'll catch you guys next time.
Awesome.